Okay. Let's say we were given this little molecule I wrote on the board, and you're like, do I have to go through each one of those carbon atoms to figure out which carbon atom is chiral? That looks like a whole bunch of work. So we're going to basically do is try to figure out how to actually break these molecules down and determine the number of chiral carbon atoms. First, we're going to just relax. Number 2, eliminate all CH3 and CH2 carbon atoms. What I mean by eliminate, it means basically like draw a light line, draw a kind of a light line through that carbon atom. Draw a light line through the carbon atom. Number 2, draw a light line through all carbon-carbon double and carbon-carbon triple bonds. Four. 3, 4. A light line through. I call all light line through all carbons with 2 or more of the same groups. Example, 2 BRs, 2 CLs, 2 CH3s, 2 CH3, CH2, etc. Now, in this molecule I drew on the board, we have how many carbon atoms? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbon atoms. And we do not want to go through all 16 carbon atoms to try to determine if those carbon atoms are chiral. First, just relax. I'm going to get this wrong, fill the class. Again, get all the bad ideas and stuff out your head. We're going to look for the molecule, we'll look for all C3 and CH2 carbon atoms. Let me get a different color marker and go through these carbon atoms. Do we have any CH3, CH2 carbon atoms? Oh, I gave everybody finish right for a second. Then we're going to ask you the same question again in a second. Next, we then going to apply those rules. I should put what are the rules number 5, what's left are the chiral carbon atoms. Rule 5. Carbon atoms are the carbons that are left. Okay. Do we have any C3, CH2 carbon atoms in our molecule? So we're going to put a green line through those. Again, I'll put a line through these. These carbon atoms are just crossed out which basically saying these carbon atoms cannot be chiral, but those carbon atoms are still there. I didn't just get rid of completely. I just basically eliminated them out as being possible chiral carbon atoms. So once I got the first rule, I got rid of my C3, CH2 groups. The next one, we want to draw a line through all carbon atoms that are double bonded. Do you have any carbon atoms double bonded?
Yeah.
Yes. Get rid of that one, get rid of this one, get rid of this one, get rid of that one. Get rid of this one, get rid of that one, get rid of this one, get rid of this one, and get rid of that one. So now by getting rid of the carbon atoms that are double bonded, I am down to 1, 2, 3, 4, 5. So I went from 16 to 5 without doing a whole bunch of extra work. That took rule number 3. Rule number 4, basically, so all the group we got left after rule number 3. We have this carbon atom, this carbon atom, this carbon atom, this carbon atom, and that carbon atom. Oops, this carbon atom right here. So you actually have 6 total still left. When I look at my first carbon atom, do I have 2 of the same groups? If you look too hard, it's probably not there. Does this carbon atom here have 2 of the same groups? My 2 of the same groups. My groups are going to be an H, a C, and an N. In my C, my first C is going to be a CH. This C is a C double bond O. Are those 2 the same C's? No. Then we'll look at the next carbon atom. We have, does the carbon atom have 2 of the same groups? What are the 2 same groups? We have a CH. This is a CH with an S, and this is a CH with an S. Because one of the CH is an S. Because when we look at CH, it's like the CH by itself, a CH, and what's attached to the CH. Are those the 2 of the same groups? Because this here is a CH was attached to 2 carbons. Because we're not the CH by itself, a CH, and what's everything CH attached to. CH attached to H, a carbon, and a carbon. This CH is attached to a H, an S, and a C. Are those 2 of the same groups? No. What about this carbon atom? Does it have 2 of the same groups? When you say 2 of the same group, what 2 groups you call them the same?
What is connected to?
So we got, what's it connected to? We're connected to a CH, a carbon with no hydrogens, a carbon with double bonded O. Any one of those 3 carbon atoms the same? No. Now we'll look at this carbon atom. Does the carbon atom have 2 of the same groups? Everybody saw every rest of them, you can say there's a C3 to C3. Everybody saw everything else, but when I saw this for here, like, no, this definitely have 2 of the same groups. I'm both of the groups with this is a CH3 group, and that's a CH3 group. But I was leading up to it, everyone saw all these other groups. When we gave the CH3 to CH3, both obviously 2 of the same groups, right? Nobody said we can't see those. These are completely different. Only thing different, they've got the bonds being different, but it's CH3 to CH3. This carbon atom with 2 of the same groups. Again, if we try to do this, it should be like a whole bunch hidden up stuff. It not be like hidden behind something. Generally, when you get the groups, it's going to be like a CH3, Br, or something like that one. It should be relatively obvious about what groups you're actually dealing with. So we're actually going to have 1, 2, 3, 4, 5 chiral carbon atoms. Yes.
So you're saying like most of the time it's gonna be obvious like that if it has the same group?
Yeah, basically we do like we try to do like a 90% rule one. It's gonna be like 2 Br, 2 Cls, or 2 CH3s, or maybe it's possible a CH2, CH3, 2 carbon atoms group both the same on both sides. Now we can get down to like even more elaborate type ones, but all we're trying to do is get like what's called like a 90% rule. Because again, we get there, if you trick you on that, if you get like one of the rare cases of it, you gotta get tricked on that one, you gotta live for that particular part of it. But for the most of the obvious ones, you kind of go through the particular rule, you get most of the obvious molecules. Basically, with this rule, you would basically get 90% of those, 90+% of those chiral carbon atoms. Again, you can get tricked on some of those particular ones, but again, sometimes you gotta live for sometimes you get tricked. In this molecule, we have 5 chiral carbon atoms. And like for us, the molecule stuff here, so each chiral carbon atom has a hand, a left hand and a right hand, which is designated by R or S. Yes.
So the C over here, like the 2 C and 2 C, we mark those out.
Let me look up for to try to keep tabs and stuff for me. Let me put a number. 1, 2, 3, 4, 5. So that I'll keep a number, you can keep it, everybody else can kind of watch, know which one you're talking about too. Which carbon atom are you talking about? 1, 2, 3, 4, 5.
Neither one of them. We had 6 in the beginning, so
Yes.
one at the top that was circled, we marked it out.
So you want to talk about this one right here. This one.
Yes.
Mm-hmm.
That one was circled in the beginning, right?
Yes.
And we marked out like
Because in rule 2, we talked about C3, CH2, and carbon-carbon double bonds. When we did that particular rule 2, we got those C3, CH3, but this molecule does not have a carbon-carbon double bond. So that was not crossed out via rule 2. I mean, we did rule 2, rule 3. Rule 2 would have not crossed this carbon atom out because this carbon atom this carbon atom itself doesn't have a CH2 or CH3 group attached. It doesn't have H2 or H3 attached to it. This carbon atom has an H3 attached to it, an H3 attached to it. We get rid of those carbon atoms. This carbon atom here, based by following rule number 2, does not get rid of this carbon atom. If I go into rule number 3, which I draw the line to all double bonded or triple bonded carbon atoms, it also still would not get rid of this carbon atom. By doing rule number 3. I will have to go to rule number 4 to get rid of this carbon atom. Does that carbon atom have 2 of the same groups? The 2 of the same groups will be a CH3, a CH3. You cannot have 4 different groups if 2 of your groups are the same. But now, was this the question you were asking me, or you were asking something else?
That was it.
But no, I couldn't get rid of when I did the first part of it, I had not applied rule number 4 yet.
Cute.
But when I do rule number 4, when I look at the molecule, it should be something obvious, like 2Br, 2Cl, or 2 of the same group one. If you got to get there, you got to go like taking a dookie on it, you're probably going too hard right there to the molecule. But again, like I said, most of the molecule stuff here is not going to be hidden behind a whole bunch of different things. Now in this molecule we have 5 chiral carbon atoms. We want to determine the number of possible stereoisomers. Then before I determine the number of possible stereoisomers, I must define something first. What do I need to define first? What's a stereoisomer? Like the number of what? I don't even know what a stereoisomer is. How can I determine the number of stereoisomers if I already know what a stereoisomer is? In this molecule for in the name stereoisomer, is there any part of that definition that we may be familiar with so far? An isomer. What's an isomer? Molecule with the same molecular formula, same atom connection. A stereoisomer. molecule with the same molecular form, same atom connection, but it differs in 3D or in space. An example will be your hands. In your hands, you got 5 fingers on both sides, like 4 fingers on the thumb. You have your thumb next to your pointing finger. You got your middle finger, your ring finger, and your pinky finger. You got the same connections on both hands. Thumb next to the pointing finger, to the middle finger, the ring finger, and the pinky finger. So both of these have the exact same little appendages. All the finger stuff has the exact same attachment. But when I try to lay them on top of each other like 3-dimensional, I will have my thumb on one side of my hand and the thumb on the other side of my hand. They basically would differ between like what side of my hand my thumb will actually be located on. The same type of molecule, because deal with chiral molecules, have the little handing this stuff to it. So basically on one side or the other side. But the same atom, same connectivity will be the exact same. You want to finish with this, how to identify chiral carbon atoms? Rule to determine the number of possible chiral carbon atoms, or possible stereoisomers. Possible stereoisomers. Two to the n, where n equals number of chiral carbon atoms. Remember, it's not 2 times n, it's 2 to the nth power. So 2 to the n power. If I had 1 chiral carbon atom, how many possible stereoisomers would I come up with? 2. If I have 2 stereoisomers, I would have 4. 3 chiral carbon atoms. It's not stereoisomers, but chiral carbon atoms. 8. I have 8. 4.
16.
And if I had 5, 32. In this molecule, there's how many possible stereoisomers? 32. 32. That's what you said. Because it's 2 to the 5 equals 32. Possible stereoisomers. Now we see this little long, drawn-out molecule. Like I said, you got to draw a long, drawn-out, complicated molecule to get 5 chiral carbon atoms in it. Then also another question comes like for biology students taking the class, like, why does a biology student need to take this organic chemistry class anyway?
Because we're at school.
Besides being in school, because basically you want to have like a reason why you take the class is because somebody told you to take it. How does this class relate to biology? We are taking biological molecule. In fact, there's a biological molecule right here too. We can take a molecule of C6H12O6. And what molecule go with the formula C6H12O6? We get, which one? Glucose. Sucrose would be a disaccharide. That could be a little more complicated one. What's that? We got glucose. Now, what's important of glucose for biology majors? Okay, energy for sugar. What sugar is the only sugar that the brain actually uses? Glucose. Like the glucose, the brain would have any food to basically starve to death. Blank out. Unless I'm wrong, is the only sugar the brain actually uses, brain cells uses glucose? We got some biology majors. Just checking, y'all, just checking. Anyone happen to know what the structure of glucose would be? So we can draw the Fischer projection of glucose. That's going to get a Fischer projection all wrong. I'm going to draw the robot OH. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. OH, H, OH, H. So look, for example, we got a glucose. We got a C6, 1, 2, 3, 4, 5, 6. How many oxygens? 1, 2, 3, 4, 5, 6 oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And the molecule glucose, which is drawn in the Fischer projection, Fischer projection of glucose. The Fischer projection kind of like a fish, like a little fish. When you take the fish, you need to kind of get the bones and stuff going both sides of the spine. It's kind of hope it can remind you of like little spines of a fish. That's your Fischer projection. In the Fischer projection of glucose, how many chiral carbon atoms do we have? Fischer can relax. We apply our rules. What are we going to eliminate out? CH2s and CH3s. Do we have any CH2s and CH3s in our molecule? Yes or no? Okay. Not this one. The only one with a CH2 or CH3 will be the bottom carbon. Cross that one out. Next we do what? Find out double bond or triple bonded carbon atoms. Do we have any double bonded or triple bonded carbon atoms? Double. One at the top. Do we have any carbon with two of the same groups? So we got carbons is left. 1, 2, 3, 4. We'll look at the first carbon. Let's have two of the same groups. It should be pretty obvious mistake. Second group, any carbon with the same groups. Third one. Fourth one. This molecule has 4 chiral carbon atoms. How many possible stereoisomers? 2 to the 4. 16. But for biology, individuals realize that sugar, glucose, does not exist in the acyclic form, it exists predominantly in the cyclic form. When we do it beta, beat them up. As far as molecule, we have the OH group on the right, attack, and kick that off. Now, if you want to, for example, you want to convert the Fischer projection into a, what is called is the Haworth projection. We're just going to cyclize this molecule. And there's a way in which you can actually put the OH group. And most of the time the class is filled with mostly female. And we always have a little thing and stuff, especially dealing with the restroom. They're always wondering who left the toilet seat up. All the OH groups to the left will be drawn up. All the OH groups to the right will be drawn down. As far as carbon atoms, it's going to be carbon 1, 2, 3, 4, 5. The sixth one we're pointing up. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. On carbon 1, is the OH group to the left or to the right?
Over here. Over here.
On my carbon atom.
Right.
If it's right, on the left is up, right will be down. Carbon number 2, I draw my OH group down. Look at carbon number 3, left or right? Carbon number 3. I'm OH on carbon number 3.
Yeah.
Left, so I draw it up. Oxygen, OH number carbon 4. Left, drawing up. The OH on carbon number 5 is actually part of the ring. Now, if you want to figure out why you have carbon number 5, carbon number 6 being up as compared to down. If you take your right hand, close it in a counterclockwise direction, where's your thumb? Up or down? Up. You can do your C2. Take your right hand, close it in a counterclockwise direction. Where's your thumb? Now take your left hand and close it in a counterclockwise direction. Put your thumb down. This will be a right-handed sugar. In biology, you refer to right-handed sugar as being a D sugar. This will be D-glucose. Since it's a right-handed sugar, all right-handed sugar will have the group pointing up, like your thumb. If it was a left-handed sugar, it would be pointing down. Now, also there's a special name carbon atom for biology, carbon number 1. What name is given to carbon number 1 in biology? Start with an A. Start with an A. Also referred to as being alpha to beta carbon atom. But there's a name, there's a stereochemical name given to it, referred to as the enantiomeric carbon. Also, again, related back to biology, so make sure you don't leave the biology people and stuff out. When I do my OH on carbon number 1, is my OH alpha or beta? And how do we tell if it's alpha or beta? Beta is beat them up. Look at my OH group. Is it up or down on carbon number 1? Up. That's beta. This will be a beta D glucose. Beta refers to the carbon number 1. If it's up or down, beta is beat them up. Alpha will be the down one. D refers to the handiness of the sugar. Take your right hand, close it in counterclockwise direction. Put your thumb up. The D1 is shown in carbon number 6 by the all been pointing up. For biology, what do we know about the sugars? Can the body make or process sugar? Process L sugars? No. But I'm doing your biology stuff. I'm trying to go organic. I'm trying to go biology with you. In fact, there's only a few organisms. I think there's like a couple of fungi or microorganisms actually even do anything with an L sugar. Most of your body will actually see L sugar like, what do you want me to do with this stuff? I don't know what to do with it. Because they have like a different array put in daylight, and actually the body would know what to do with an L sugar. But again, the reason why I'm trying to point out the stereochemistry one is that even a molecule glucose, you have a whole bunch of chiral carbon atoms. In fact, glucose not only has 4 chiral carbon atoms, it actually has 5. So we'll start next to the chiral carbon atoms of glucose. It already had 1 being chiral. We had carbon number 2 being chiral. Carbon number 3 we already said was chiral. Carbon number 4 we said was chiral. Carbon number 5 we said was chiral. And we got a new chiral carbon atom, which is carbon number 1. In the original molecule, carbon number 1 was not chiral. Once you cyclize it, does carbon number 1 have 4 different groups attached to it?
Yeah.
So instead of actually having 4 chiral carbon atoms, glucose in the cyclic form has 5. Which gives you how many possible stereoisomers? 32 of them. And guess what we're going to do before this class is over? We're going to end up naming all 32 RS configurations for glucose. Yay! Everybody seem all happy. We're going to do all 32. And we're going to do it with a pattern. But again, one of the reasons why I'm doing like far as the little stereochemistry as far as like talking about for biology. Another reason why I'm dealing with the little stereochemistry. Anybody watch these little medicine commercials on TV? And the ones I can remember, I did like a thing called it was like a foot fungus type one. And which like a thing called dairy to get some of your nail beds and kind of attack and stuff right here. And you can actually treat this little fungus with some kind of fungicide type thing. Now one of the little side issues to me called liver damage and even death. I'm like, shit, I like to have nice looking fat toenails, but I don't want to end up having liver damage and die because of some toenails. But also know, like a lot of times you get some medicines and you get all these different side effects. You gotta take another medicine to take care of the side effect. The reason why you get all these different side effects is because of those stereoisomers. If you look at the molecule glucose, there's 32 possible ones, but it's actually you're going to end up only coming up with 16 in actuality. Because one going to be the L and the D for us, L sugar and D sugar. But again, main reason for the medicine stuff right here is that chiral carbon atoms. Those things put a monkey wrench up into the body when they actually put the wrong one in. Even for something like ibuprofen, which is like for Tylenol. You actually have the R and the L configuration for the molecule. One is good, one is bad. Usually, the best case scenario, you have like one that's is good and the other is just not horribly bad for you. Also, what we try to do is come up with the RS configurations for the possible stereoisomers. Determining configuration of these stereoisomers. First we're going to start with a stereoisomer with one chiral carbon atom. Remember, for each chiral carbon atom, it must have its own letter. If there's one chiral carbon atom, I would need to have one letter. If there was 2 chiral carbon atoms, I would need 2 letters. If there were 3, I would need 3 letters. If there was 4, I would need 4 letters. So we're going to start with our chiral carbon atom. You can start with one letter. You can either start with R or S. I do like to start with the letter R. Again, you can start with the letter S. I recommend whatever letter you start with, keep that letter the same all the way through. I'm going to start with the letter R. What's the mirror of R? There's only 2 letters, R and S. The mirror of R would be S. If I had one chiral carbon atom, I would have two stereoisomers. One would be R, another one would be S. One chiral carbon atom. If I had two chiral carbon atoms, how many letters would I need? Two. We're going to start with both being the same. We make both of them being R and R. What is the mirror of R, R? S, S. Next, I'm going to change one letter at a time. I'm going to change my first letter, and I'm going to keep the second one the same. I'm going to change one verb at a time. So I'm going to start with my saying RR, and I'm going to make it S for the first letter, keep my second one the same. If I were to mirror this, it would give me RS. If I had two chiral carbon atoms, I would have four possible stereoisomers. This is a set of two. That's 1, 2, 3, 4. Those are the letters that belong to those four possible stereoisomers. Your four would be RR, SS, RS, or SR. Those are your only four possible combinations. Any combination besides that will just be redundant to what you already did in the past. Now, what if I had three chiral carbon atoms? How would I do my combinations? For three chiral carbon atoms, yes.
So for that one, is that 2 times?
Because for every number, every letter, for every chiral carbon atom, I need a letter. Only letters I have is R and S. Here I have two letters, both R and R, and I mirror that, I get S and S. This is 1 and 2, one set of 2 and another set of 2. Then I do my next one. I'm going to start with my RR. I'm going to change one letter at a time. I'm going to change this from being R to S, and I keep my second R being the same. All I do is change one row at a time, make it easy to follow. Next, I'm going to take that same group and we'll mirror that. The mirror of S will be R, the mirror of R will be S. This is my third set of 2s and the fourth set of 2s. You would do one for 3? We should do one for 3. If I have three chiral carbon atoms, how many letters would I need? 3. I'm going to start with the same letter all the way through. I will have R, R, R. Mirror of R, R, R would be S, S, S. I'm going to now again start with my same R, R, R. This time I'm going to change the first letter. I'm going to start with, so now I'm going to change the first letter from being R to being S, R, R. I change one letter at a time for my basic one. What's the mirror of S, R, R? It would be R, S, S. Notice what I did. I took my initial one, I changed the first letter. This time I'm going to start my initial one again. This time I'm going to change the second letter. R, S, R. Mirror of R, S, R would be S, R, S. Notice I went and changed my first letter, changed my second letter. Next I'm going to do what? Change my third letter. I'm still starting with my same basic one, R, R, R. So it'll be R, R, S. Mirror of R, R, S will be S, S, R. One set of three, two sets of threes, third set of three, fourth set, fifth set, 6, 7, and 8. These are your 8 possible RS combinations for a molecule with 3 chiral carbon atoms. Isn't that fun? But can you see how we have to get to the pattern? Notice I'm not trying to jump around everywhere. I'm not trying to just run around with a chicken like chicken with head cut off. I'm trying to have a pattern to the particular one. So we start building to even more higher molecules. We can start doing the same letters. Three chiral carbon atoms. Let me go back here and put 2 chiral carbon atoms. Now, wasn't that fun? We're going up to 8. Next, we're going to try to do one with 4 chiral carbon atoms. I'm going to need some help for us this one. Dime, you up? Dime, you got my back. I'm just going to kiss one card. So now we'll do one with 4. Again, we're going to have a pattern to it. We're not going to just jump around everywhere. We have 4 chiral carbon atoms. How many letters do we have? 4. Every chiral carbon atom must have its own letter. I'm going to get back into the corner. We have R, 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 R. Mirror of R, 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 R. S, 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 S. 4 S's. S, 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 S. What am I going to do next?
Yes.
Start my same 4 R's, just I'm going to change the first letter. So it will be S, R, R, R. Mirror of S, R, R, R.
R is this.
Would be R, S, S, S. Notice I changed my first letter. Next, I'm going to take my same 4 R's together. I'm going to change the second letter. So it'll be R, S, R, R. Mirror of this will be S, R, S, S. Notice I changed the second letter. Next, I'm going to start my same basic 4 R's, and I'm going to change the third letter. So you have R, R, S, R. Have to mirror S, S, R, S. Now up to 8. Finally, I'm going to do what? I'm going to change my 4th one. So it will be R, 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 S. Mirror will be S, 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 R. Totally so far I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 14. Remember, we're going to have how many? 16. Next, I'm going to change the first two. Go my same RRR, and we'll change the first two letters. So it'll be S, S, R, R. Mirror, R, R, S, S. That will give me 11 and 12. Since I changed my first two, next I'm going to change my middle two. R, S, S, R. Mirror would be S, R, R, S. 13 and 14. Here going to come the fun one. I did my first two, my middle two. What do you think I should do next?
Last two?
The last two will not even work, but I'll show you the last two. If I did the last two. R, R, S, S. Mirror this will be S, S, R, R. Have we done this already?
Yeah.
11 and 12 are the same thing as that number. If you look for here, this is S, S, R, R. These two are the same. And this two also be the same. You had to do the change the first and the third.
Oh.
To get this one, change the first and the third. Change the first one to S, R, S, R. Mirror will be R, S, R, S. And that will be 14, will be 15 and 16. That will give you 16 of them. But glucose has 32 of them. To get the other 30, to get the other 16 for glucose, remember there was the new chirocarbon atom, which is alpha and beta. You have 16 with alpha and 16 with beta. That's how you get your 32. So you got 16 with the little number 16, you have alpha, alpha, alpha for all of them, and you get 16 with beta, beta, beta for all of them. Or beta for all of the rest of them. And that will give you a total of 32. But we're not going to do all 32 in a particular molecule. It takes too long to do 32. We're going to get potentially up to, now we can get up to 4. It's actually assigned the chirocarbon up to 4. 4 carbons. Isn't that fun? Remember also you had like a molecule on the board and we had those 5 chirocarbon atoms in it? What I want to try to do is one that's not quite as many as 5. But I do it as a molecule called penicillin V. And we're going to determine how many chirocarbon atoms the molecule have present. And then we also want to assign the RS configurations to the chirocarbon atoms. So that molecule penicillin V. If not, I got to make up something similar to it. I would like to have a real one. More penicillin. I got one similar to for like one off hand. This is actually be similar to what penicillin B would end up being. In this molecule, we're going to determine the number of the carbon atoms. Without going through the whole process again, we will have, cross that out, cross that one out. Cross this out, and cross that one out. That's what I'll come up with. And it's okay, I come with 4 of those. But in this molecule, come with 4 carbon atoms. We want to assign the 4 carbon atoms. The 4 carbon atoms are 1, 2, 3, 4. And those 4 carbon atoms, what do we know about our molecule? Those carbon atoms are actually part of a ring. Are we going to have to change our rules up to account for the ring? No, we won't. We're like to do our rules. We're going to first do carbon number 1. What atoms are directly attached to carbon number 1? What I like to do, I like to start from the top and go clockwise. So carbon number 1, what atoms are attached?
Hydrogen.
We got a hydrogen, going clockwise, carbon, nitrogen. Next, we're going to arrange our atoms according to atomic number. Hydrogen, carbon, nitrogen. What is the highest atomic number? What atom has the highest atomic number? Nitrogen, making that 1. Second highest, we'll make that 2. Other carbon also will be 2. And we got hydrogen will be number 4. We're going to rank 1, 2, 3, 4. Because there was a race and there was 4 people in the race and 2 people got in a tie. The next person after the 2 people in the tie will not be number 3. They'll be number 4. Right, so the race was a tie, and the people who came in second was tied together. The next person behind it will not be number 3. The next person behind it will be number 4. So now we try to figure out, will carbon number 2 and carbon number 2 be the same, or there's a difference between the 2? Going clockwise, we go to the first carbon atom. What atoms are directly attached to the first carbon atom? H, a S, and a C. Attached to the first one is an H, S, and C. Okay, there's a tie. Next, I will go to the carbon atom at the bottom. What groups are attached to carbon atom at the bottom? You have an oxygen and you have a carbon. Now, the way we treat it is double bonded O. We treat any double bonded atoms, we treat it as if there were 2 single bonded atoms. So we treat the double bonded O as if it was an O, a O, and a C. Have we lost you so far? Remember what we had as far as the attached carbon atom will be H, a C, and an N. Those are the 4 groups attached to this carbon atom. We wrote them down, H, a C, and an N. Next, we're trying to find out as far as, we have a tie between 2 carbon atoms. Since the carbon atoms are a tie, we got to go to what is called a tiebreaker. We have to look and see what each of those carbon atoms is attached to. Attached to my first carbon atom, I have an H, a S, and a C. Those are the 3 atoms directly attached to the carbon atom. The 4th, yes?
So, the First, number 2, under N.
We got N. We got the carbon, this is carbon now. Which one are you referring to? You talking about
That one.
this one? Mm-hmm.
So you saying that, why are you worried about that?
Yeah.
That's what you're worried about.
No, because this is my carbon atom right here. When I put a star beside it. This is the carbon atom. This carbon atom is directly attached to an H, attached to a C, attached to a C, and attached to an N.
Okay.
Those are the 4 groups attached to the star carbon atom.
So you don't really ignore the cross out C.
Only thing across the C that says, well, that's why I say it's not eliminated. I just took it out for being part of a bit of chirocarbon atom. It can't be a chirocarbon atom, but it's still there. I can take the molecule, rip it apart, and throw it away. Just basically eliminate it out that says, in determining if the carbon atom was chiral or not, it's not a chirocarbon atom. But it's still part of the molecule. It's just, it's not in my writing to be a chirocarbon atom. Got it.
So why wouldn't you look at, like, okay, we got carbon number 1, that's the attachment,
So you're looking at this right here. I'm looking at this carbon number 1. I'm just looking at what's attached to it.
that's attached to it. So why wouldn't the tie be between carbon number 2 and number 3 instead of carbon 2 and that carbon that you crossed out?
Remember, from here, it's carbon number, you said carbon number 2 and 3. Carbon number 3 is not attached to the star one.
Oh.
I'm looking at what's attached to the star carbon. This is what's attached to the star carbon atom, an H, a C, and an N. Those are the ones attached to the one that's starred. I can't jump to over here yet, because it makes me just dealing with one. I'm looking at what atoms attached to that atom I'm focused on with the star. Those are the 4 atoms to the star carbon atom. Now, on this star carbon, the way I try to do it, kind of go clockwise in my pattern so I know which one is which. The first carbon atom is going to have attached to it an H, an S, and a C. The next carbon atom is going to have attached to it a double bond O. We treat a double bond, any double bond atom as being 2 single bonded. So we got an O, and a C. That's what's attached to the second carbon atom. I want to make sure we can at least see that far, because I'm trying to. I don't want to go too far without you seeing how we got those particular arrangements. Because all I'm really looking for is carbon number 1 right now. Just carbon number 1. Everybody see how I got attached to carbon number 2, a H, a S, and a C. To carbon number, the second carbon atom, we got an O, and a C. Now, in this particular arrangement, we want to cross out similarities first between the 3 groups. And our 3 groups, are any atoms the same in our 3 groups? For our 3 groups for here, between this 3 and that 3, are any atoms the same?
The carbon.
There's a carbon. So we'll cross out similarities. Boom, boom. Once we get the C's out, all the atoms are the same, we got rid of those. Now we have no similarities between the 2. It's not like everybody can gang up on each other. We pick for each group a champion for that group was remaining. The group that remained is going to be a sulfur versus a oxygen. Which one has the highest atomic number? Sulfur versus oxygen atomic number. S versus O. Which one is it?
You say highest.
Your highest atomic number?
So,
Sulfur. Sulfur becomes group number 2. The other carbon atom becomes carbon number 3. So what I can do is put my little groups already label them. Rid of all the stuff. We got a 4 box that one. The next one's going to be a 2 box. The next one will be a 3 box. And this is 4. I mean, this is 1 box. If I do my little order, I got a 4, a 2, a 3, and a 1. Those are my prioritized. I prioritize the 4 groups attached to the carbon atom. What are we going to do next? Do a curved line connecting 1 to 2 to 3. You can ignore 4 in your connection from 1 to 2 to 3. We're going to connect 1 to 2 to 3. What direction are we going in? Clockwise or counterclockwise? Clockwise, which would be what letter? R. This here is the relative configuration. What group get the final say so?
4.
Group 4. Is group 4 forward or backwards?
Backwards.
Dotted line indicates backwards, solid line forward. Like when it's a solid punch, that's coming at you. This here would be R, because it stays being R. And notice my little R there, and I pointed to the carbon atom I'm referring to. I ain't got a little teeny tiny one like I'm trying to scare it or to hide it. My thing, you're going to be wrong, Don't be wrong, and then can't be even right, scared being right. So that was the arrangement for carbon number, carbon 1. Next we'll look at carbon 2. I'm just going to do 3, I'm not going to do all 4. For carbon number 2, different markers. I'm going to look at carbon number 2. What atoms are directly attached to carbon number 2?
S, H, H, S, and C.
We got H. We have S. We have C. And we have C. And then I'll reach my these off a little bit. So we have our, we're going to rank our atoms according to atomic number. What's the highest atomic number between H, S, C, and C? S will be 1. Number 2, 2 carbons, 2 and 2, and hydrogen is number 4. We have a tower with the carbon. To the first carbon atom, we have attached to it a H,
C,
a C, and a C. H, a C, and a C. Attached to this carbon, to the third carbon atom. Now this is the third carbon atom. We have a H, a N, and a C. H, a N, and a C. We're going to cross out similarities. Carbon, carbon, hydrogen, hydrogen. So now we got carbon versus nitrogen. Which one has the highest atomic number between carbon versus nitrogen? Nitrogen, making that group number 2, and this other group becomes group number 3. I'll pull a different shape as far as the rank between which one I'm doing. Number 4, put a triangle. I can put out a red. Talk about different colors. Number 4. We have number 1. We have number 3. And we have number 2. What are we going to do next?
Our circle.
Take a curved line connecting 1 to 2 to 3. 1 to 2 to 3. What direction am I going in?
Counter
Counterclockwise, which would be
is
S. But who gets the final say so?
4.
Group 4. Is group 4 forward or backwards?
Backwards.
Backwards would mean the configuration stays as being S. And then I do a little line, big fat letter of S, and point to the carbon atom that I'm referring to. But you guys, if you're wrong, be wrong, but don't be trying to be all scared about fitting answers. No, there's only 2 possibilities anyway. Either R or S. You got a 50-50 just by guessing at something. Next, I'm looking at carbon 4. What atom is represented carbon 4? We have a C, a H, and a C. How's the atomic number? The C's, all will be 1, 1, 1, and that's 4. Ooh, make it tough on us right here. Relax. This is when we start here, going from the top clockwise. Attached to the first carbon atom is what 3 atoms attached to the first carbon atom? We got what atom? S, C, and C. Not an H, because H don't come yet. H is not directly attached to the carbon atom here. H is attached to the next one, but not attached to this carbon atom. So we have to the top one, we have a S, a C, and a C. Next we go to the carbon atom at the bottom. What atom directly attached to this carbon atom?
Carbon.
This carbon atom. We got an O, and an O. This carbon atom here is the same one all of them got in common. So I'm not just counting that one. Because if I don't count this, we give it 4 groups. You have to then count this carbon atom here also. You can count it, but if you want to count it for one, you got to count it for all of them. So you're going to have the next one, an O, and an O. Next, I'm going to look at this carbon atom here. How many atoms are attached to this carbon atom? 3. We got an H, a C, and a C. H, a C, and a C. Are there any atoms common with all 3 groups?
No.
No. So there's no atoms common with all 3 groups. We're going to pick a champion from each group. From group 1, what's the atom with the highest atomic number?
S.
S. Sulfur going to represent the first one. In the second group, what atom with the highest atomic number?
Oxygen.
Oxygen. Oxygen represents this group. And the one at the bottom, which atom has the highest atomic number? Carbon. Carbon is going to represent the bottom group. Of the 3 atoms, sulfur, oxygen, carbon, which one's the highest atomic number?
Sulfur.
Sulfur. That will be the outright number 1. The next one, between oxygen and carbon, oxygen what makes this group number 2. And the last one will be group number 3. Put a blue marker. This will be 1. This here would be 2. This group is 4. And number 3. We're gonna connect the lines from 1 to 2 to 3. 1 to 2 to 3 will go in what direction?
Counterclockwise.
1 to 2 to 3. What direction?
Oh, okay.
Clockwise, which is R. Who get the final say so?
4.
Group 4. Is group 4 forward or backwards? Forward, so the configuration would be
Is
S. And draw an arrow to it. Check it and see it. Wasn't it funny? Yes. I could draw, we can draw 4, I mean, all 3 if you like.
Yeah, that was confusing. How did you guess if there's no first the third one? Because there's only like 3 atoms attached with O times 2.
Well, I'm very smart, so to jump off, let me actually see number 3. Darian.
How do you not get lost in how to remember the number?
This is what I said, what I recommend as far as doing this here, don't put them all together. Take them out there and just basically do like 3 separate pieces. And that way keep track of, because it does get really complicated by putting all this little stuff on the board, as far as like scribble scrabble. It gets very confusing about how they put it together. What I recommend doing is just take one carbon atom and then take every carbon atom and put them aside. And write them out. Look, for example, I'm going to do number carbon 3. I'll put on the junk here. So I put all the stuff here because again, it does get really confusing about where's all this little markers and stuff going to. I'm going to do carbon number 3. I'll put a C. Attached to the carbon is going to be a C, a H, and a C. Notice for here, I'm not going to try to worry about as far as like, am I getting the exact same direction? On carbon number 3, I got a carbon. On the other side, we got a C. Here we got an H, and that will be a C. As far as the kind of a rough estimate about where the group stuff located at. I got one on the top, one on the left, one on the bottom, and one on the right, one on the left. So what I did is still have to try to put all the groups together. Just when they say molecule, I just kind of took it out and bring it to the side.
And draw a dash just in case.
Now you put a dash for you just make sure you know what group the hydrogen atom is. Not with, but the same dash it was to begin with it.
Yeah.
Now I'm going to look at each group. Look at the carbon at the top, which is a tie. What's the test of the carbon atom at the top?
Hydrogen
We got an H, a S, and a C. Going to this carbon atom. What's the test of this carbon atom?
C.
We got a C, and an H. Carbon, carbon, H. Going back to the other carbon atom, which is over here. What's the test of this carbon atom?
2 O's
And a C. So we got an O, O, C. Do any of our groups have 3 atoms in common? You got a carbon. So cross out similarity. Carbon, carbon, carbon. This is group number 4. Since there's no atoms that are the same anymore, we're going to pick a champion from each group. For the carbon at the top, what represents the carbon at the top?
the S.
For the carbon at the top, S. Carbon over to the right, carbon C. And then one to the left, oxygen. Between sulfur, carbon, and oxygen, which one has the highest atomic number? Sulfur making that 1. Second highest.
Carbon.
Carbon, oxygen. Oxygen, making that number 2. Third highest will be carbon 3. Next, I'm going to connect 1 to 2 to 3. 1 to 2 to 3. I'm going to go in what direction? Clockwise or counterclockwise? Counterclockwise will be what letter? S. Who gets the final say so? Group 4. Is group 4 forward or backwards? Backwards, so the S stays. This will be S configuration. Isn't that fun?
Yeah.
But again, so always, if you take your time with it, don't get all panicky. Also, like something you start doing, you can't be in a rush. A lot of times you get, if I'm in a rush, like 2 seconds, I'm gonna be done with it. Relax. Take your time and stuff, do the process for you. I'm not gonna give you 8,000 of these particular ones, but for the ones you get for here, just kind of get yourself relaxed. Go through your process, and the answer will come out right, consistent, the same way all the time. We want to make consistent. We want you to at the end of the day be consistent. We're going to have you consistently right and consistently wrong. If you're consistently wrong, it'll be much easier to tweak you and get in the right direction to get you consistent being right. We don't want you like every day with like one day I'm right, tomorrow I'm wrong, and I'm kind of flip-flopping back and forth to the random type of one. Again, we have a process to go through. We'll go through our same process again, make us all OCD. We want to do the exact same step exact same step the same way every individual time. Much easier to follow. Jasmine.
I was still trying to figure out why this one right here didn't count.
So find a carbon atom.
This one?
Does it have 2 of the same groups?
Yes. That's all.
You cannot have 4 different groups if 2 of the groups are the same. Because carbon only have 4 total bonds anyway. You're talking about that carbon atom.
Yeah.
It has 2 of the same groups.
This one has the CH, that one has the CH.
It's not just atoms, same groups. Not the same atoms,
Okay.
same groups.
Gotcha.
Now, wasn't that fun? Non-superposable or stereoisomers. Enantiomers are stereoisomers. Stereoisomers. That are non-superposable mirror images. Now, what is superposable? Superposable means like identical. So they're non-identical. Superposable means identical. Now, if you want to use the word identical, like non-identical, instead of using the word non-superposable, I'm not mad at that. But again, when you want to mention the word superimposed, this means all they're referring to means is the word identical. That are not identical. So it's like a mirror image when you try to line them up together, they're not identical. For diastereomers, are stereoisomers that are non-superposable non-mirror images. And you probably, what kind of what are you talking about? I'm trying to get someone to kind of mirror me. We're going to have Kate. So Kate will mirror me. When I put my, I want you to put this, to mirror me as far as putting your arm up. In the mirror, just be able to me as far as like an arm. You can scratch your head too if you want to. Scratch your head. This video would be a mirror image of each other will be considered to be enantiomers to each other. to be a diastereomer, I'm gonna put my right hand up. I want you to put your right hand up. Now, if you're in the mirror, you're basically like, hold up, in the mirror, and I'm just a reflection of me, and I put my right hand up, and your mirror put the right hand up, you're like, hold up. I might want to start thinking about getting out of this little bathroom and getting out of here. Because, you know, your mirror should have the same arm. Your arm on this side should still be, the mirror should have the arm on the same side too. And that, the diastereomer will be having like, kind of like the mirror, which basically half your body will be the same, the other part will be like different. You have like identical part, then the mirror image part. Also, what we're going to do is actually show you the drawing of, draw a molecule that will be, for example, draw a molecule and draw the enantiomer and the diastereomer of a particular molecule. And how we actually going to go ahead and do the particular molecule. Before I finish, there's a third relationship, and that will be meso. I can make redraw meso, make it bigger, as far as higher up. Are stereoisomers. That are superimposable mirror images. And I also explain about what I'm also drawing a structural molecule of a meso, so you kind of see what I'm referring to. Here we drew a molecule on the board. Does that molecule have any carbon atoms in it? How many total carbon atoms do we have on the molecule, in the molecule that I drew on the board? How many carbon atoms do we have total? 4. Can we eliminate out any carbon atoms being excluded from being possibly chiral?
Yes. Yeah.
We can get rid of the first one and we can get rid of the last one. Do we have look at our two carbon atoms? Does any carbon atom have 2 of the same groups? No. No. If I want to draw the enantiomer of this molecule, I draw a mirror. H and O will mirror each other. Got C and H. We have a bond, got a C. The BR will mirror the BR. The SH will be on the other side. We then have a C, double bond O, OH. For the carbon atom not chiral, doesn't matter if it's left or right or something like that. We'll keep it the same direction. We only really focus on is the chiral carbon atoms anyway. And you're going to put HCH3. The relationship between these two molecules will be enantiomers to each other. They are mirror images that are not identical. But all I do is kind of put this line here, kind of represent a mirror. If I do a mirror, whatever closest to me, the mirror will have that also being closer. If I have like a little fist pointed out, the mirror will always have a fist pointed out. I'm not gonna have a fist pointed out, the mirror will have a fist pointed back in. So basically, like whatever the mirror will be, if I'm here, the mirror also is pointing the same direction. That's why I kind of draw a line as far as the mirror. These two will be enantiomers. For a diastereomer, if you were to draw a diastereomer of this molecule, Again, I start my same basic molecules. See the word O, OH, C, C, CH3, OH, H, BR, SH. To draw the diastereomer. For the diastereomer, I'm going to mirror one of my two carbon atoms, and the other one I'm going to keep identical. It doesn't matter which one you actually mirror, which one you keep identical. Because actually you're going to have two possible, you can have, in this case here, two diastereomers. Just like basically saying, like, does everybody do like cousins? Remember there's only be like brothers and sisters, only one brothers and sisters, but you got a bunch of cousins. You actually have more than one diastereomer molecule. In this case, you're going to have at least two. You got one, you have at least two of them. But again, for the diastereomer one, you can access two possibilities. What I'm going to do first, I can either mirror the first one and keep the second one identical, or I can keep the first one identical, or I can keep this first one identical and mirror the second one. There's actually two possibilities. You can actually do both of them if you want to, or all I really need is when the exam is one of them. So what I'm going to do, I'm going to actually mirror the first one. I got my C, mirror will be BR, SH. And I'm going to keep the second one identical. OH, H, CH3. Notice in this molecule here, I kept one group being the mirror, and the second carbon atom, I kept it being identical. So whatever it was, the OH pointed in this direction, I kept the OH pointing in the direction. And the H on the same side, whatever the bottom point here, kept kind of like, I'll keep my bottom half of my body being identical, and the other half kind of flipping it over. Now notice for here, there's actually two possibilities. Notice for here, I end up mirroring the top one and keeping the bottom one the same. You also equally could have written as far as the diastereomer. I'm going to keep the top one the same and mirror the bottom. So I have a C, double bond O, OH. I'm going to keep the top one identical, BR, SH, and I'm going to mirror the bottom. OH, H, and CH3. This molecule and that molecule are diastereomers. But what is the relationship between molecule A and molecule? Got molecule A, molecule B, and molecule C. Molecule A and molecule B would be a diastereomer to each other. Molecule A and molecule C would be a diastereomer to each other. What is the relationship between molecule B and molecule C? What is the relationship between molecule B, and molecule C? Molecule B and molecule C are enantiomers to each other. The relationship between molecule B and molecule C. If I do molecule B and molecule C, if I took them up here and kind of roll it over and put them side by side to each other, you will see that molecule B and molecule C are mirror images to each other. The relationship between molecule B and molecule C will be enantiomers to each other. Anybody see that or anybody not see this? Between the relationship between molecule B and molecule C. If you took basically, easy way to do it is kind of take them and kind of put them next to each other. Like do a line and stuff, you kind of put them next to each other. Easy way to do it is kind of put a line, take the molecule here, put a line, and then take other molecule and put it next to it. And see how they relate. Are they basically going to be both the mirror image to each other, or one will be mirror image, one will be identical? Yes.
Okay, so you said that molecules A and B and A are both
Diastereomers.
diastereomers, but B and C are mirror
of each other. So B and C, look at B and C, if I take molecule B and molecule C, those are related. They'll be an answer to each other. They'll be mirror images to each other. But in relationship to as far as if I give out a couple different molecules, molecule A and molecule B will be diastereomers. Molecule A and molecule C will be a diastereomer. But if I ask for what is the relationship between molecule B and molecule C, that relationship would be enantiomer.